Hello everybody, this is the last little video that I'm going to do about this week's class, and we're going to go a little away from the computation of convex hull, but not that far. In fact, when I explained to you the algorithm to compute convex hull, there was always a geometrical question that was asked at each iteration of the algorithm. That was the following question. We were asking ourselves if we have 2 points, P1 and P2, in the plane, okay, and a third point, P3. We were asking ourselves whether the turn from P1 to P2 and then to P3 was a clockwise turn or a counterclockwise turn. Here, you see, it goes that way. It's a clockwise turn. Okay? And so, how could we as a question, we could compute angles. Okay? This is extremely expensive, this is not very good. And another way to see the same, to ask the same question, would be to compute the signed area of this triangle. What is the signed area? It's the area of the triangle which would be positive if the triangle is, oriented counterclockwise, and will be negative if the triangle is oriented clockwise. Here, the triangle is oriented clockwise, so if we use the right hand rule, it's in fact normal points downwards. It's easy to see that if P1 has coordinates x1, y1, P2 has coordinates x2, y2, and P3 has coordinates x3, y3. Then the signed area that I'm looking for, which is in essentially a predicate that I call orient 2D, okay, the value of the signed area is equal to a simple determinant. It's one of the exercises of the book at the end of chapter 1. I give you the answer. It's simply that, easy to remember. It's 1, 1, 1. It's x1, x2, x3, y1, y2, y3. So computing this determinant, okay, when I put the vertical, determinant of that matrix, gives you the answer we're looking for. So if this thing is negative, okay, it's a clockwise turn. If this thing is positive, it's a counterclockwise turn. If this thing is 0, it means that the 3 points are exactly aligned. So if P1, P2, and P3 are exactly aligned, then this determinant is exactly 0. That's the problem we have. Because exactly aligned is something which is not, which is true, could be true when we are dealing with exact computation, exact arithmetic. We are dealing with computer arithmetic, IEEE IEEE norm for storing double precision numbers, and here we'll see it's not sufficient to provide robust algorithm for computational geometry. So, how could we make a little experiment, computer experiment, that would show the issues related to machine precision and this simple predicate, computing simply if an area points, if a triangle is positively oriented or negatively oriented. We'll do a little experiment that does like that. Imagine we have our coordinate system. I'm going to put 3 points, okay, like that. And this point is exactly 12, 12. This is 24, 24. And this is 0.5, 0.5. Of course, if I give these 3 numbers these 3 points in the predicate, it should give me 0. They are aligned. Okay, they are on, okay, the bisectrice of the first quarter. So it's quadrant. So they are aligned. So what I'm going to do, I'm going to zoom. Okay, I'm going to zoom here around this point. Okay, I'm going to zoom very much around this point. You'll see how much I'm zooming. I'm zooming a lot. Okay, and around this point 0,505, I'm going to put a little grid, a square grid. It's a square grid. It's in the middle. Okay, the point is really in the middle of the grid. Okay, and this grid will be extremely small. Okay, so I'm going to put a very, very small grid like that. Okay, and this grid, the size of the grid is the epsilon machine. Okay, so the size of this grid, okay, the size here of the grid is epsilon machine, which is 2 to the power minus 53, which is probably something close to 1.110 to the minus 60, something like that. Okay, so this is the epsilon machine. So when you think about it, all the points here on the diagonal here, I didn't do a right diagonal, but anyway, all the points on the diagonal of this thing, okay, so all those points are aligned with the 2 other points, 12, 12 and 24, 24. So if I am asking if this is point A, if this is point B, and this is point C, remember, right? Okay. I am asking to do a orient sorry. I have to move that. I want to do an orient 2D of A, B, C, and A belongs to that grid. Okay, A belongs to that grid somewhere here. What I should, and I am going to look at all the points of the grid here. So what I should see at the end is a thing like that. Here, I should have an answer that says, okay, I have A, okay, which is on the top, B, C, like that, A, B, C. Okay. So A, B, C is oriented here counterclockwise, okay, and if I put A here downwards, okay, okay, so this is clockwise. So I should have an answer here, which is counterclockwise, and hold this thing here. It would be clockwise here, and it should be 0 on the diagonal. Okay, but here don't forget that the points, the grid around point A, 0,505, is super, super, super tiny. But it's still, I'm going to have a grid, let's say, which will be something like 1,000 times the machine precision. So the point which is the further away from the diagonal will be at 10 to the minus 13. So it's not so bad. But let's see what it gives as a code. So let's go into the code section. Okay, so here I'll give you that code. Okay, so here I have simply put the 2 points 12, 12, 24, 24. My point A, which is the center 0,505, and I compute the modified point, which is A plus I multiplied by epsilon. Okay, and epsilon is, okay, equal to the power of 2 to the power 53, which is my machine precision, epsilon machine. And so now with that, I should be able, so with my grid, I should be able to have the result I present you on the slide, okay, which is essentially a matrix with downwards we have positively oriented, upwards positively oriented, downwards negatively oriented, and 0 on the diagonal. So let's see what this gives. So here I will show you what's my O-test. So O-test is there. Okay, it's not there, it's there. So O-test computes this determinant, okay, and this is the thing I showed you. So it's the simple test that computes the vector product, the z component of the vector product, okay, and if it's positive, then I say okay. If it's negative, I say it's negative. Okay, simply. So I compile it. Okay. Not robust. Okay. And I do it. And I say I do a grid of 1,000 by 1,000. So it's a little too much. Let's do 500 by 500. And let's see what this gives. Okay. So let's go back to that one. I did something wrong, sorry. Okay. Oh, I didn't save, sorry. Oops. Let's do it again. Okay. Not robust. Okay. That's beautiful. Okay, let's see. So what you see is my grid. So you see here, I did the reverse. I did negative for counterclockwise and positive for clockwise. So it doesn't matter that much. But here you see on the top, everything that is blue is saying it's oriented in a certain fashion. Everything that is red is oriented in the other fashion. And everything that is green says my triangle has a 0 area. What you see here, so the grid is 500 by 500 like that, you see that we are having a huge amount of error close to the diagonal. You see here that some of the points that were supposed to be with red are blue, some of the points which were supposed to be blue are red, and a lot of the points that were supposed to be red or blue are green, which means that you compute a 0 area where the area is not 0. And of course, the difference is very small. But as I told you before, in computational geometry, having 3 points that are close to be aligned is very common. So this algorithm, if you write the algorithm, is a very naive way of computing the predicate, will lead to a huge amount of errors. So how could you fix that? So in the code that I have 2 fixes, but I'll show you the easiest one is, like usual, use a library. So there exist robust predicates, okay, in the air. I'll give you a way of doing that. So for example, here, if you look, I have a robust predicate, and it's a robust way of computing this area. So here, I'm going to use those predicates. So it's a simple library. You just use that library. I'll give you the code. It's easy. I replace my simple orientation test here by the robust orientation test. So I compiled it again, and I call the program now robust. And that's robust with the same, bam, and let's see what it gives. So we'll see the difference. Here, what you see is essentially that it's perfect. It's absolutely perfect. It gives me exactly the right answer, okay, up to machine precision, okay, which means that if you look very closely, the first little blue square that you see here is the one below the diagonal, above the diagonal and below, and it gives exactly the right answer. So the last question we would like to ask, and it's a very important question, is in the case of convex hull, I don't want an answer which would be points that are aligned. I want an answer which will always be either red or blue. And there is a solution to that, okay, which I will talk about a little later in the course. But for doing a simple convex hull, if you read the book, and I leave you reading the book, there is a way to avoid this configuration by simply considering in the convex hull, if you have 3 points that have the same angle, for example, that they are all in the convex hull. It's easy to decide. But when we'll talk about triangulation, this will not be possible anymore. We will have to make a choice. And then I will finish the discussion about the robustness, adding what is called symbolic perturbation to the points, which always, in this case here, always gives an answer which will be yes or no, but not perhaps. Okay, either the triangle is positively oriented, negatively oriented, clockwise, counterclockwise, but never flat. Thank you. This video is done for me.